This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Hello everyone. I've lost my voice this morning, so sorry if it's not really clear today. So we're going to start the lecture number 4 in FEA today. So if you remember from the Tuesday workshop, we derived the element stiffness matrix and global stiffness matrix for the simplest element type, which was a linear spring element. And then we applied the boundary condition like the zero displacement at one of the nodes, and then calculated the other equations based on the external forces. So what we're going to learn today is pretty much the same procedure, but for different element type, which is called truss element. If you remember from the second FEA lecture, truss element was one type of the 1D elements. So in 1D elements, we have two types. One is the truss element, and the second one is the beam element. In truss element, we can only have axial forces, while the beam element can withstand the axial, the moment, the torsion, and the transverse loads. So after finding the element stiffness matrix for one single bar or truss element, then we try to assemble the global matrix and solve an example and apply the boundary conditions. So again, we want to use all these 8 steps for deriving the equations and the K-matrix, either global or like the elemental K-matrix for bar element. So first, just look at the shape of the bar element. So as you can see here, this is one single bar element, which is subjected to the opposite tensile forces at the ends of the bar element. We want to use linear element since therefore we only have 2 nodes at each end of the bar element. And the initial length of the bar element, like the spring, is L. So this is the first step, right? Choosing the type of the element. The second one is select the displacement function. So again, since we want to go for linear displacement function, make it easier to derive the equations, we can just write down the only degrees of freedom for each node, which is in direction of the x-axis, u, in terms of the nodal values, which are u1 and u2. So it's exactly the same procedure that we've done for the spring element. If you want to write it down in general form, u would be u equals a1 plus a2x, which is a linear function of the x. Since we have 2 degrees of freedom, 1 degree of freedom for each node, then we have 2 unknown coefficients, a1 and a2, pretty much the same as the spring element. So the procedure is exactly identical. So what we need to do is just make sure for this equation, by putting the node 1 in the equation, means x equals to x1, it will give us u1, and at node 2, this equation gives us u2, which are the nodal values. So by applying the boundary condition, we get to this matrix form. And if you remember, n1 and n2 are called shape functions, and they are exactly identical to what we obtained for the spring element. So after that, we need to know what's the relationship between the S-strain and displacement, and also what's the relationship between the S-strain and S-rest. So in the spring element, it was very easy to find the relationship between the force and the displacement directly, right? F equals to spring constants times to the deformation of the spring. But in the element, in the truss element, would be a little bit more complicated. So assume that the bar element is made of a linear elastic material. So the S-strain, since we only have one displacement, which is in x direction, epsilon x, or S-strain in x direction, equals to du by dx. And if we assume that the element length is small enough, we can approximate it by the elongation, or u2 minus u1 in the bar element over the initial length of the bar element. And by assuming the linear elastic material, S-rest would be proportional to the S-strain by the Young modulus. So sigma x equals to E, which is Young modulus, times S-strain in x direction, epsilon x. So just remember that why we need to write down these equations. The general formula for the finite element analysis is F equals to K times D. F is the force, K is the stiffness, and D is the displacement. So we want to write down the relationship between the force, which are applied onto the bar element, and find out their relationship with the nodal displacements, u1 and u2. In other words, here we want to know what's the relationship between T and u1 and u2. So this is the figure of the bar element. So the tensile force, based on assuming that the S-stress is uniform all over the bar element, T will equal to sigma x times cross-section of the bar element, sigma x times A. And then if we substitute sigma x with the Hooke's law, which is the linear elastic equation, E times epsilon x, and then substitute the epsilon x by u2 minus u1 over L, this would be the equation for T. Is it clear, guys? Great. So then, if we just, again, what we did for the spring, we break down the element and the nodes to two nodes, node number 1, the element itself, and node number 2, and then try to write down the force equilibrium equations in all these components, you will figure out that little f1x would equal to minus t, and f2x would be t. These are the force equilibrium equations at node number 1 and 2. So now, we want to know that what's the relationship between f1x, 2x, and u1 and u2. So we only need to substitute this equation into the into the equations for f1x and f2x. So I'm going to give you a couple of minutes. Just try to write down the equations for f1x, f2x in terms of u1 and u2, and then try to write it down in matrix form and just obtain the element K matrix. All right. Has anyone got the K matrix for the bar element? Is it similar to the K matrix for a spring? If you just take out like the K outside the K matrix, like the spring constant. So if you substitute the equation for T, AE times U2 minus U1 over L for F1x and F2x, these would be the equations, right? And then if you write it down in matrix form, this would be, the middle matrix would be the element stiffness matrix for truss element. It's very similar to the K matrix for the spring element. So in the spring element, if you remember, it was K, and K. If you just take out the K from the K matrix, it would be pretty much the same. Just K equals to AE over L. So AE over L is the constant. It's like a spring constant, but for the truss element. All right. It's so easy, like the spring element. So here is an example that we want to solve. So we have a rod which the two ends are fixed, totally fixed, and we want to use three elements for analyzing this figure. So we have three elements. Each element has two nodes. In total, we have 4 nodes. And the only external force which is applied on this rod is at node number 2 with 3,000 pounds. So we want to know that what's the displacement at nodes number 2 and 3, and what are the reaction force at node number 1 and 4, which are the fixed points. So the type of element is obvious, right? It's truss element. We want to use linear displacement. We know the K matrix for each individual element. So we only need to calculate A times E over L for each single element. Two of them are exactly the same, I guess. Yeah. Element number 1 and 2 are with the same material properties and the geometry. It would be a little bit different for element number 3. Once we got the little k, the element K matrix for these 3 elements, then we need to come up with the global matrix and just introduce the boundary conditions. All right, I'm switching to document camera. We just learned that for for the element K matrix or little k matrix, it was A times E over L times this 2 by 2 matrix. So now, since element 1 and 2 are having the same properties and the same geometry, the little k matrix would be the same for them. The superscript means the element number. This is cross section, this is the Young modulus. And this is the length of the elements. I'm using the same equation for element number 3. Just the cross section and the Young modulus would be different. But in the end, the K matrix is all the same for these 3 elements. So if I want to determine the corresponding nodes in each element, for element number 1, the nodes are node number 1 and 2. So this is 1, this is 2. And for the element number 2, the nodes are 2 and 3. And for the third element are 3 and 4. the reason that I wrote these numbers, the node numbers for like each column of the little k matrix is to make it easier for doing for calculating the global k matrix. So if you remember from the Tuesday lecture, there are two ways to calculate the global k matrix. One was just doing exactly the same that what we did for the element one, just writing down the equilibrium equations, force equilibrium equations for each node and the elements, and try to find out the relationship between the forces and the displacement. And the second approach, which was much easier, was direct approach. So based on the node numbers in each element and knowing the element k matrix for each element, we can assemble the global matrix. All right, so before coming up with the global k matrix, the first thing that we need to figure out is what's the size of the global k matrix. Can anyone remember that how we calculated the size of the global k matrix? Exactly. So you need to look at how many degrees of freedom we do have here. So like one displacement per node. So in total would be 4 degrees of freedom. So I'm going to draw a blank 4x4 k matrix for capital K. Column 1 is corresponding to node number 1, 2, 3, 4, and the same for the rows. Right? Now we got the size of the global k matrix. The second point that we need to be careful is we need to determine the common nodes. So I'm going to bring up the problem one more time. So this is the configuration of the elements at the node numbers. So which nodes are common like in 2 elements? Node number 2 and node number 3. So these are the nodes that we need to be very careful about them. And from this, we can just realize that there is no relationship like between node number 1 and 4 directly, or even between 1 and 3, or 2 and 4, right? They're not connected to each other directly. Right. All right. Why don't you spend 2 minutes to just write down the global k matrix for me? Try to find the components from the little k1, little k2, and little k3. All right, was it easy? So the common nodes are node number 2 and node number 3. So I'm going to start with K1, the little K matrix for element number 1. So this is K11, this is K12, K21, and K22. All right, I'm going to put it here. And then going to the next little K matrix, which is exactly the same, but this time it's K22, K23, K32, and K33, right? So I'm going to put all these 4 nodes here. K22, I have already put one component for that, so it's going to be +1, -3, -3, and 1. And the last element K matrix is for node number 3 and 4. In other words, this is K33, this is K34, and this is K43 and 44. So +1, -1, -1, 1. And if you don't have anything to put for the rest of the components, just put 0 there. This is 0, 0, 0. Sorry. 0, 0, 0. Right. So we assemble the global matrix. Now the next step is introducing the boundary conditions. So let's have a quick look at the problem that we want to solve. So what we know from the boundary condition here is 2 nodes are having 0 displacement, right? Node number 1 and node number 4, which means U1 and U4 should be always 0. And the other thing is, we also know that we have an external force at node number 2, which is 3,000 pounds. Right. So now let's see how we can implement these loading and boundary conditions. So this is the general FEA formula, right? Capital F are the external forces, and U1, U2, U3, U4 are the displacements. So we know that U1 and U4 are 0. Sorry. Right. And also, we know that F2x is 0, F3x is 3,000 pounds.
Where do the negatives go in the K matrix?
They're gone? Yeah. Yeah. Thank you for pointing out that. All right. Thank you. Probably it's like a problem in this slide as well. All right. Is it right now? Yes. Right, so keep going. So we know that U1 and U4 are 0, and F2x is 0 because we don't have any external force there, and the only external force at node number 2 is 3,000 pounds, exactly. Right. So one way to solve these equations is to expand the matrix form and then substitute U1 and U4 with 0 and substitute F2x with 3,000 and F3x with 0, right? But I have another way to do it, which is much faster. Whenever you have zero displacement, just be careful. Whenever you have zero displacement, then you can omit the row and the column corresponding to that node number. Right? So here, U1 and U4 are zeros, right? I can delete row number 1, column number 1, row number 4, and column number 4 in the K matrix. All right, let's do it together. This is gone. Don't need you. Don't need you either. Right. Then just make it very simple to a 2 by 2 matrix. Don't cross it out very thickly because we need them later. We don't need it now. Right. So then what would be here is we only need to solve these equations. F2x, F3x equals to 10 to the power 6 times this 2 by 2 matrix and times by U2, U3. And then we can substitute the F2x and F3x with 0 and 3,000 pounds. So this would be the final displacement at node number 2, and U3 would be 0.001 inch. So this was the first part of the question. What are the displacements at node number 2 and 3? The next question is, what are the reaction forces at node number 4 and 1? In other words, what are the capital F1x and F4x? So now that we know all the nodal displacements, we can simply go back to the general FEA formula that we crossed it out like the rows number 1 and 4 and columns 1 and 4, and then find out, just expand it and find out what's the equation for obtaining F1x and F4x. Right, I'm gonna write it down at the bottom of here. So F1x would be this, and then by substituting U2 here, U1 is 0, this would be F1x. And the same way, we can calculate the reaction force at node number 4.
Shouldn't be minus.
Yes, you're right. Sorry, I don't know why what's happened to the negative signs. And the same for that one, right? Which basically makes sense. So if we just go back to the, where's the question? Can't find it. Yeah. So this is the quiz. This is the. I mean, this is good. This is the basically that you're. I mean, this is about the calculation. I know about it. But if you just made a mistake, like what I did here, like miss a sign, and the last step in the solving the FEA equations was interpreting the results. So I mean, you obtain f1x or f4x. I mean, no matter like the sign now. But the thing is, you can see here that we just pulling node number 2 in positive x direction. So which means that the reaction force should be negative, right? I mean, these are some clues that to make sure that you've done the calculation properly. Any question about this example? Yes?
How do you know F3x is 0?
F3x 0?
Yep.
Because all the capital F, like F1x, F2x, and so on, they're showing the external forces. But it doesn't mean that we don't have internal force there. So little F1x, little F3x are the internal forces, and they're absolutely non-zero. Does anyone know that how we can calculate, this was a good question, how we can calculate the internal forces? Yes, or just simply just using the FEA formula for the individual element. So for example, for element number 1, we can say that little f1x, little f2x equals to 2 by 2 K matrix for the element number 1 times u1, u2, right? It's exactly that how we got it from the free body diagram, but you can just use that formula, just avoiding doing the free body diagram again. Yes?
For the local matrix, for the local element, the local matrix is the internal force.
Yes, exactly. For the local K matrices, like little f equals to little k times little d, this is just showing the internal forces. But in the global formula, capital F showing external forces. Right. So this is how we did it, and just form the global K matrix. There's some negative sign missing here. I'm gonna update this slide. So yeah, and that's it. So the next question about this is a very quick question about this example is, what if someone asks us to calculate the displacement at a point which is not basically at node numbers? For example, here, we want to calculate the displacement at x equals to 40 inch, which is not at node number 2, either at node number 3. So it's between these two node numbers in element number 3. So how we can calculate the displacement there? The first thing that you need to ask yourself is, what formula we need to use to calculate the displacement here? Exactly. So if you remember, in step 2, we assume a linear displacement function, which was about the linear shape functions as well. So we want to use that thing here. But just be careful that, this is the shape function. Just be careful here that in the displacement function that we drive in the beginning of this lecture, it was about the U1 and U2, right? That one was general for each individual element. So here, the node numbers for element number 2 is 2 and 3, which means that we need to substitute U1 by U2, U2 by U3, right? Using the nodal values at node number 2 and 3 here. And then since we know the values for U2 and U3, and x is equals to 40 inch, the location of the point that we are interested to calculate the displacement, and this would be the final results. By assuming that the displacement is changing linearly within the element. Any questions? Yes?
The value of 40 in the bottom formula, should that be 30? Because it's the linear value for L.
So 40 is the location of the point that we want to calculate displacement, right? 30 is the location of the node number 2, right? So in the formula, which is the linear displacement function, instead of the x could be from 0 to 900 inch, right? This is the range for x. Right? So we are interested to know the displacement at location x equals to 40. That's why we substitute the x with 40 inch. But this formula is only for this part of the bar, just between node number 2 and node number 3, within the element number 2.
Yeah, so if it's for that part of the bar, why is L 90 and not 30 instead?
Can you say it again?
So if it's for the part of the bar from node 2 to 3, why is L 90 but not 30?
Why don't we just use element 2 rather than
Yeah,
out of
is it the length of the whole bar or the length of the element?
No, this is the x. X is the absolute coordinate of the point.
Yeah, understood. Yeah, but
No, his question was like capital L.
yeah,
Denominator of 90 instead of
Oh, no. That formula is only for the element. So, oh yeah. Yeah, that's right. That's totally right. That should be 30. Yeah. So I'm going to fix that thing as well. All right, thank you so much. What's that?
L is 30, shouldn't X be 10? Yeah, more than.
times 10
I'm going to fix it, so I'll let you know in the next lecture. It takes a lot of time now. Right, so the next topic is, what we learned about the driving the K-matrix was for the bar element, which was positioned horizontally, like along the x-axis. So now what will happen if the bar element is like inclined or tilted as compared to the x-axis or y-axis. So now how we can derive the local K-matrix and global K-matrix? So the thing is, we need a transformation matrix to transform the local. I mean, we're still able to use the previous element K-matrix, like the 2x2 K-matrix that we got in the coordination of the x prime and y prime. But if we want to know that what's the component of the K-matrix in the global coordinate in the x and y coordination, that would be another story. So we need the transformation matrix to transform the K-matrix from the local coordinate to the global coordinate. So we're still able to use the element K-matrix, little K-matrix that we obtained for the local coordinates in terms of the x prime and y prime. So again, f prime equals to k prime times displacement, which is all good, so we don't have any problem with that. But if we want to use it in the global coordinates, that would be a little bit tricky. So we want to calculate the f equals kd in the global coordinate. So one point that we need to pay attention here is when we are in the local coordinates, we only have 1 degree of freedom for each node, right? Only displacement like in x prime direction, u prime 1 and u prime 2. But if we decompose u prime 1 and u prime 2 in terms of the x and y, in the x and y coordinates, u and v, then it will show up 4 components, right? 2 degrees of freedom for each node. So u prime 1, if we decompose u prime 1 into u1 and v1, this would be the equation, and the same for the displacement at node number 2. So now imagine that we just write down the 2 previous equations in terms of the matrix form. So C stands for cosine and S stands for sinus, sinus of theta, the degree between the element and the global, like the x direction of the global coordinate. So we call this matrix transformation matrix, or T. And similarly, we can transform all the nodal forces in local coordinates into the global coordinates. By using the same transformation matrix. And then we can just substitute the f prime by t times f, and the same for the displacement in the local coordinates, and just transfer it to the global coordinate. And now what we want to find out is if we just bring the transformation matrix from the left-hand side of the equation to the right-hand side to the equation, and then write it down in terms of the like a simple formula f equals kd, what would be the k matrix in global coordinates in terms of the k prime and transformation matrix? So to do that, to bring the t matrix to the right-hand side of the equation, we need to invert it, right? to invert the t, you know that there's a condition there. The matrix should be square. Otherwise, we cannot calculate the inverse of like a rectangle size matrix. So that is why that we need to also add the v'1 and v'2 into the equations as well. Although they are 0, we don't have them. We don't have these two components in the local coordinates, but we put them there to make the calculations possible, right? By using the two green equations, which are v' and v'2 in terms of the u1, v1, and u2, v2, the transformation matrix would be like this. So this is a square, and now we can simply just calculate the inverse of the T matrix. So if you write it down in terms of the local coordinates, like f prime x and f prime y, so y rows number 2 and 4 are 0 here. This is in the local coordinate. Can anyone tell? Exactly. Since in the truss element in the local coordinate can only withstand the axial forces, right? So we don't have them. We only put them there to make the transformation matrix square, and then we can calculate the global K matrix. So if you do the calculations, and since the transformation matrix is orthogonal, which means that the inverse and the transpose of that matrix are the same, then this would be the K matrix for one individual element in the global coordinates. So this is a 4x4 matrix. The reason that, we know that the bar element only has 2 degrees of freedom, so it should be 2x2. But the thing is, when we convert it to the global matrix, we also have displacement in y and x directions at the same time. So that's why it would be a 4x4 K matrix. All right, thank you so much. Sorry for the problems with the negative signs and the things. I'm going to fix them, and tomorrow we'll go through all of them quickly. Thank you so much, and I'll see you tomorrow.
When we try to for the local this one. Yeah. So
you want to calculate the internal forces?
yeah, I want to make sure it's true. Here, F3x, I use the same U3 and U2 we found.
Yes, exactly. Yeah, because displacement is the same. Doesn't matter internal or global. You know what I mean?
Yeah. But here, F3x, is it the nodal force, or is it the one on the element itself? The internal one here we calculate here. Is it on node 3, or it's because this is obviously
On both of them. It's acting on both node and the element.
yeah, but the direction is opposite.
All right.